Jnanam paramam dhyayam. Knowledge is supreme.
So, let us begin our today's lecture. We will just recall what we had done earlier. We had looked at what is called the linear span of a set of vectors. So, given a subset S of Rn, we defined what is called the linear span. So, this is a linear combinations of the vectors in S, that is C1, V1 and so on. Okay. So, this we called as the linear span of the vectors. So, we looked at some examples of the linear span, and then we defined what is called a basis for before defining the basis, we showed that there can exist more than one sets such that the linear span of the set B is equal to linear span of S. That means, if a set spans a vector space, it is possible that a subset also spans that vector space. Right. So, this motivated us to define what is called the basis of a vector space. So, a basis was defined as a set of vectors whose linear combinations give the whole vector space, and there is no proper subset of it which gives the linear combinations as the vector space. So, a basis is a minimal set of generators. It is a given a set, it should generate everything. So, every vector in V should be a linear combination of it, and no proper subset of it should generate it. So, no proper subset of it should give linear combinations all of them. So, such a thing we called as a basis of a vector space, and we gave examples of basis of vector spaces. So, basis of a vector space need not be unique, that is what we said. So, given a vector space, there could be more than one sets which form a basis. So, the questions arise, does every vector space has a basis? How to find a basis of a given vector space, and what is the relation between any two bases of a vector space? Right. So, given a vector space, first question we would like to answer is, does it always have a basis? Right. Second, does it how to find that basis given a vector space, and what is the relation between any two bases of the vector space? So, let us observe one thing to start with, that basis, if a vector space, if a set B is a basis, then 0 cannot belong to it, right. Then this 0 cannot belong to the basis. Right. If it is there anyway, because it is not going to do, so we will remove it. So, a basis will always have, because it is a minimal set. So, if B is a set of vectors which is a basis and contains 0, then we can delete 0, right, because given any vectors we can take a linear combination 0 times V1 plus 0 times, that will give you 0. So, linear span will always have 0. So, if it is 0 is a part of a basis, then it is not minimal. So, we can always remove it to make it a minimal. Right, and definition of basis is a minimal set. So, 0 will never belong to the basis of a vector space. Okay. So, we want to show that every vector space has a basis. So, the idea is following. So, let us look at a proof of this. So, theorem is, if V is obviously a non-zero vector space, a vector space, then there exists a basis for V, right. So, let us look at a proof. So, V is not equal to 0 and V is contained in Rn, right. So, we start with it as a set of generators, right. So, let B contained in V be a finite set such that the linear span of B is equal to V. Right? We have got a set of generators and we want to check whether it is a basis or not. So, what is the possibility? So, one possibility is case 1, that B is minimal, that is, what is B minimal means? There does not exist any proper subset such that linear span of B 0 is equal to V. Then what will happen? That means we are saying that this set itself is a basis. So, that is B is a basis. So, what is case 2? So, case 1 was it is minimal. So, what is the second possibility? It is not minimal. So, suppose B is not minimal. So, that means what? If it is not minimal, that means at least there is one vector, right, which we can remove. So, let V belong to B be such that if I take the set B and remove from it V, then the linear span of B minus this V will be equal to V, right. If it is not minimal, then at least one vector is redundant, we can remove it, it is not required. So, let us say that a vector is V, which is in B, which is not required, right. So, look at, so it is not required, that means what? B minus that vector should give me everything, right. So, again two possibilities, either this B minus V is a basis once we have removed that one vector which was not required. So, one possibility is after removing one vector it becomes a basis. If not, again in B, so if not, then there exists some say u 1 belonging to B minus V, which can be removed, right, like we removed earlier one vector. So, there is one possibility again that there is a vector which we can remove. So, if we go on doing this process, what will happen? Right, this set B is a finite set, right, the basis is a finite set. We removed one vector, we removed another vector, right. So, eventually you cannot remove everything, eventually there will be one vector left at least in the last stage if possibly, then that single vector will give everything, right. So, after finite number of steps, so let us write, so after finite number of steps, we will get a set B 0 which is contained in B such that linear span of B 0 is equal to V and B 0 is minimal, that is B 0 is a basis. So, what are we saying? We are saying that you have got a vector space which is generated by some set of vectors B, that may not be minimal. I can make it minimal by removing one at a time, which are vectors which are not required. So, that will say that eventually you will get a set which is minimal and will generate. So, that is essentially the idea of saying, right. So, let us I wrote B and here in the slides it is S. S is a set V 1 V 2 V n such that the linear span of S is equal to V, right. Obviously, we can assume 0 does not belong to it, because if it belongs we can remove it. Okay. Now, two possibilities arise. S is a basis, that set itself is a basis. If not, then what will happen? At least one of these vectors V1, V2, Vn is not required. So, let us say that vector is Vj. So, remove from S that Vj, and the span of that. So, the square bracket also indicates the span of linear span of S minus the vector Vj is V, right. So, once you have removed one, again check whether that is a basis or not. If not, remove another one if required and go on doing it. So, after finite number of steps, right, in finite number of steps you will get a subset of S which cannot be reduced further, and that is a basis, because S is only a finite set. So, you cannot remove everything, you can one by one you can remove at the most n minus 1 and the process will stop. So, that shows the existence of a basis. So, basically what we are saying is, if V is a vector space in Rn, it has got a set of generators which is finite, then you can go on removing which are not required to get a minimal set of generators, and that is a basis, right. So, let us give some equivalent ways of describing what is a basis. So, V is a vector space which is of course non-zero, and B is a set which is V1, V2, Vk contained in V. So, we want to give different ways of looking at when this set B can be a basis. We have already defined one definition as minimal set of generators. So, the first one is B is a basis, that is a minimal set of generators, and we are going to show it is equivalent to saying that every element V of the vector space V has a unique representation as a linear combination of elements of B. So, let us prove that. Let us prove that the 1 and 2 are equivalent. So, equivalence of 1 and 2. So, what does the equivalence mean? That means, if I assume 1, I should be able to prove the statement 2. If I assume statement 2, I should be able to get the statement 1 from it. So, let us look at one way implication. The first one, 1 implies 2. Let us look at that. So, what does the statement 1 gives? So, let us say let B is equal to V1, Vk be a basis. So, that is, so what is this is what is given to us, that is the linear span of B is equal to V and B is minimal, right. To show what is to be shown, statement 2, and the statement 2 is every vector V belonging to V has unique representation, right. So, let us suppose not. So, suppose not. So, suppose, so what is the negation of the statement 2? That means, there is at least one vector which has two different representations. So, suppose there exists V belonging to V such that this V is equal to sigma alpha I V I and also equal to some other scalars beta j V j, j equal to 1 to n. Okay. So, we are assuming there are two possible representations. Okay. So, what is our aim to show? It is not possible, that means each alpha I must be equal to the corresponding beta I, right. So, let us assume, so suppose there exists some j between 1 and n such that alpha I alpha j is not equal to one of them, alpha j is not equal to beta j. Then from this equality we will have alpha j minus beta j V j, take out that where these two are not equal, I can write it as sigma of minus sigma of alpha j minus beta j of V j. Oh no, let me write I equal to 1 to n, but I not equal to, on one term I have taken on the left side, everything else on the right hand side. Is it okay? From this is equal to this. So, if I bring it on this side, so alpha I minus beta I V I summation is equal to 0, right. So, is it right. So, I take the other things on the other side, I not equal to j, right. Is it okay? I am just taking one term on one side, everything else on the other side, right. So, what does this imply? This implies V j can be written as minus 1 over alpha j minus beta j summation I not equal to j alpha I minus beta I V I. Note that alpha j is not equal to beta j, so I can divide by that, right. That is what we assume. So, but that means what? That means V j is a linear combination of V 1, V 2, V j minus 1, V j plus 1, V n, right. This V j is a linear combination of the remaining V i's. So, that means what? That means from the set B, if I remove V j, I do not lose anything, right. I can get everything. So, linear span of this is equal to the whole of V, right, because V j itself is a linear combination of remaining. So, all the remaining ones will do the job, but that is a contradiction, not true. Why? What is the contradiction? Because what was given to us was 1, it is a minimal set, I cannot remove anything from it. So, not true, because B is minimal. So, hence 2 holds. So, what we have shown is 1 implies 2. Let us show the other way around, namely 2 implies 1. So, let us prove the other way around statement. So, 2 implies 1. So, given what is the statement 2? Statement 2 says every element has unique representation, right, in terms of elements of B. What we have to show? B is a basis, that is to be shown, right. That is statement 1, that B is a basis. So, note, first of all we note every element has got a unique representation. So, note clearly linear span of B is equal to V, right, because every element is representable, in fact uniquely. So, it spans anyway. So, what is left to be shown? To show it spans and to show it is a basis, that means I have to show it is minimal, right, to show B is minimal. Suppose not, that means what? There exists a V belonging to V such that if from B if I remove V and take the linear span, that is equal to V, right. Okay. So, now look at this vector V, this V is not equal to 0 first of all. Why is not 0? Because from B we have removed, right, V cannot be 0, because if it is 0, B did not contain 0. So, nothing is removed then. So, it is not 0 and V belongs to L of B, Ls of, right. B belongs to the linear span of B, right, implying what is V equal to, it should be a linear combination of something. So, let us say it is sigma L of I V of I equal to 1 to n for some alpha I is scalars, right. But that means what? If I take everything on one side, V minus sigma alpha I V I equal to 1 to n is equal to, what is it equal to? The 0 vector, right. Everything else on I transpose on one side, shift everything on one side is 0, but what is 0 also equal to? It is 0 times V 1 V, right, minus 0 times V I, right. I can write 0 as a linear combination of anything by putting all scalars 0. So, but here it is a 1, right, V is 1 cross 1, 1 cross V. So, I have got on this side a linear combination where all the coefficients are not, all the constants involved in the linear combination are not equal to 0, is equal to another linear combination where everything is 0. So, what does it contradict? That means 0 has got two different representations, its representation is not unique, but that contradicts 2, right. So, not possible, because 2 says every element has unique representation, right, and we are given for 0 two different representations. So, hence, right, so it says hence 1 holds. So, this proves, what does it prove? This proves 1 is equivalent to 2, 1 implies 2 and 2 implies 1. So, that was a statement we wanted to show here. So, in the theorem, the first statement is B is a basis, it is a minimal set of generators, and we have shown it is equal to saying that every element is representable as a linear combination of elements of B, and that representation is unique, there is only one way of doing it.